In the year 2009, the Scandinavian VHF meeting was at the place Knottebo here in Sweden. At that meeting, there was an instrument from Rohde Schwarz, an FSUP, and I had brought an oscillator there to measure the sideband noise, and this was the result, and it was not in agreement with what I had measured at home. And this led me to make a study of different oscillators, and I traveled to Stockholm to do measurements with this FSUP instrument. And as it turned out, the error that was between my measurement and the FSUP was because we were not aware of the important thing. Harmonics have to be below 30 decibels below the carrier. And my harmonics were much stronger, and that caused an incorrect result. You can find this article at this location. Here is an earlier video about sideband noise measurements with Linrad and the hardware that I'm using also in this video. I brought 5 oscillators to Stockholm for measurements on the FSUP. This was one of them. That's the one I had at Knottebo, now with a low-pass filter on it, because otherwise it wouldn't measure properly on the FSUP. And this is another one. And this is a better oscillator I made after the Knottebo meeting in order to do these measurements in Stockholm. Here they are. I have stored them for 15 years without changing anything in them. I am using these SDR-IP units. They are phase-locked to these two 10 MHz oscillators, because the SDR-IP 80 MHz clock can be phase-locked to 10 MHz. And these two oscillators are in turn locked. This is the master, and this slave is phase-locked with a very long time constant, defined by this big electrolytic capacitor and a large resistor. I want to compare with the FSUP measurements from 2009. So I have set these parameters for the SDR-IP units. I have set the bandwidth of 4 Hz, and the window is number 9. It's a flat window with a Gaussian error function on both sides. It gives a very ugly shape in the frequency domain, but it gives very good suppression of aliasing spurs when changing the sampling rate in the frequency domain as I'm doing. And of course enable correlation spectrum too. And the FFT version should be number 6. For the baseband, I have currently set no down conversion. It means I'm running the baseband at 64 kHz, like the original frequency from the SDR-IP units. Maximum baseband storage time that allows many averages on the demodulated noise spectra. I have set the correlation graph to show in the logarithmic scale on the x-axis, and rather quickly I get this result. I can clear the graph so you see how it behaves. And here, where the noise is strong, so correlation makes no difference. It has converged after, 15 seconds or something. And it will take quite some time to get the flat noise floor out here. But before I do that, I have to calibrate the SDR IP units because I want a flat frequency response from plus minus 25 kilohertz about from the center. Here is the calibration routine running. I can see here the amplitude response has a wiggle. I cannot say how much it is, but maybe 1 dB or so. And I want to get rid of that. The phase response is very flat. And here is the response after calibration. There is a small amount of noise on it, but it's very flat now. Those undulations are gone. The frequency response is very flat now. You can see 0.2 decibels per division. But there is a discontinuity at the center. So I have to press C here to remove the center discontinuity. The center discontinuity is narrow, so I only want to exclude a small section at the center from the digital fit, from the polynomial fit. That means I want to go down from 500 Hertz to, say, 200 Hertz. And that is L and 200. And then continue. And what I see here, yellow is the data I have, and red is the difference to fit it. And I have to magnify by pressing plus. And you can see that on the right side of the green line there is some strong feature. That is what I want to remove. And I remove whatever is on the right side of this blue line, so I have to move that. Pressing R. Well, too far. Left. So from here to the end. So I just press A to accept this. And here things look very good. So I really don't want to replace anything. So I place the blue line as far as I can go with it and accept that. And here is the symmetric power on the audio side, and it looks very ugly because this is the amplitude correction that I need to make the spectrum flat. And I want to remove those points that go up here. So I want it to extend in a nice fashion. That means R for the blue line. Like this, and accept that. And here is the last item, and it is symmetric phase on the RF side. And like that, A. And here is the new curve, and we don't see that notch at the center anymore. I can see here on the phase curve that this is the region where something was fitted. So S to save. Finally, I want to remove noise from the calibration function. That is function D. And Linrad suggests that I should use a 64-point function. That means I am losing 0.4015 of the pulse energy, and that is probably white noise, because the periodicity of the undulations, well, maybe I should go for 128. This isn't really very critical. Here is now the frequency response. I can see a small problem here at the center, and since it is 0.2 decibels per division, I can think that this is maybe 0.03 or something like that. It's small, and the phase error is also very small. And further, I will not put the carrier exactly on this frequency. At this fairly high sampling speed, in the baseband, 64 kHz, I cannot set a larger transform than 12 here, because I'm doing filtering in the time domain to avoid problems in case the carrier comes at the sides of the filter. Filtering in the frequency domain is much faster, but has problems occasionally. So I cannot make a very narrow filter, which means I cannot look very close to the carrier. The closest I come is about 270 Hertz or something like that. Now, to compare with the FSUP that starts at 1 kHz, that's out here, this will be perfectly okay. So now I have to wait, because the noise is at this level, and it's about 106.75. My own measurement long ago was -169. And now I have waited 13 minutes, and I don't see yet the result at 10 kHz. It looks like it will come out something like around here. And that is -173. So it will be interesting to see at higher sideband noise levels whether my system is in agreement with the FSUP or if there is a systematic error that I have here. Here is the result from the FSUP for the old reference oscillator. I have placed the mouse right between 170 and 180, and I think it is reasonable to say that this curve, if we even out the noise, is right between the mouse and the 170 line. So I make it -172.5. And at 1 kHz I say 160. After 1 hour and 11 minutes, I have good enough statistics to read out what the phase noise is according to Linrad. At 1 kHz, I see 160.0. And at 10 kHz, that's where the mouse is now, right between those two lines. Once more. These two lines. That is -172.5, with some little uncertainty, but not so much. When I set a linear frequency scale, I can read at 10 kHz. Here, quite accurately, I would say 172.5. And I can see some irregularities of unknown origin. I have now connected the VCO, the oscillator, with an LC circuit where the capacitor is a capacitance diode. It is very much more noisy, as you can see from the waterfall. And here is the phase noise. It comes very fast. This is after not yet 1 minute, it's 50 seconds. Now it's 1 minute. And I have very good statistics immediately. And here, with 1 decibel per division, I can see that at 1 kilohertz, it's on the line of minus 119. And at 10 kilohertz, the decimal is 0.3, and it's 143.3. The next one, with the label FM on it, is a similar VCO, but with a common design error, in that the capacitance diode is fed through a resistor rather than through an inductor. And therefore, the noise of the resistor adds noise to the frequency control of the oscillator. This one is very noisy, 20 seconds, and I have no noise in the measurement here. So I see I have to expand the scale to read it better. So at 1 kilohertz, 93.3, and 10 kilohertz, down here, right on the line of minus 126. This is a crystal oscillator with a common design error. It has a buffer amplifier which is noisy. At 1 kilohertz, this AM modulated box is at minus 147.8 or so. But at something like 15 kilohertz, there is a minimum, and then the noise goes up. I suspect this is caused by an output impedance that is not 50 ohms. So this reading could be affected by that. It is at minus 168.5. I will insert an attenuator to see whether things become more likely to be correct. With 6 decibels of added gain and 10 decibels of attenuation with this attenuator, which is pretty good, and also increased sensitivity of the 2-channel receiver, I should have the same signal level as before into the SDR IP. But the impedance has to be much closer to 50 ohms. But still I have a problem here. It doesn't look like the noise from an oscillator. Well, it could be, but it seems odd. Anyway, I take down the numbers, 148.3 maybe, and down here 167.3. There could be correlated digital spurs in the SDR IPs. Look at this thing which changes with time. It's a spur and it goes up, and then after a while it's going to go the other direction. So that is some synchronous spurious signal from the FPGA, I would guess. and now it comes negative, and it goes far down, and then it goes up again. So that is some peculiarity. Here is the amplitude noise, minus 133.7 at 1 kilohertz, and at 10 kilohertz, it's on this line, 138.0. And minus 138 dBc per hertz is my old measurement from 15 years ago using the Perseus, and assuming that the only noise is the amplitude noise. When looking at the waterfall, I can see that the noise is much stronger on the lower side, and I can see that here also. It's whitish on one side and red here. I can make it more visible, I guess, by changing the scale setting. Like that. It's obvious that the amplitude noise and the phase noise, they are correlated close to the carrier at least at half a kilohertz up to 1 kilohertz or so. And it's clear they are correlated, and the angle between the modulations, the phase angle, is 45 degrees one way or the other, because yellow and white traces are at the same level. Correlation decreases as frequency increases. And I don't remember how it was computed, if this is because the level here is much lower than the level here. I have forgotten the details. This just shows that there is a correlation which can be used to reduce the phase noise with appropriate amplitude limiting and filtering. Now I'm looking at this. It was my new reference oscillator 15 years ago. At 1 kilohertz I see 172.5. And at 10 kilohertz, that's here, that is 179.5. With the linear frequency scale and compressed fairly much and expanded the Y scale, this looks more like 179.3. But that decimal is not very precise. And I have waited for 15.5 hours to get this result. The amplitude noise is very low. At 1 kilohertz I cannot see it because the imaginary part goes from here to here, something. And this is a bug. I haven't erased old pixels, but I will fix that. At 10 kilohertz I start to see the white noise out here, and I will probably see it better if I compress, if I go to linear display on the x-axis. This looks like minus 184 at 10 kilohertz. The SDR-IP units suffer from fairly strong amplitude noise close to the carrier, and that's why this measurement is so noisy. The level is at the same order of magnitude as the phase noise. In 2009, the value I had from my measurements with, I think, the Perseus was minus 179.5. And that is in perfect agreement with what I found now. We were not able to measure with the FSUP, probably because we didn't have the time to wait for 12 hours or more. But I don't know whether there could have been some other limitation. When I compare the new results I've found with Linrad with the old ones from 2009 with the FSUP, I find a very good agreement.
The difference, Linrad and FSUP at 1 kHz, the difference is 0. And the same here, it's 0. Here there is a difference of about 1 decibel for the unit labeled VCO. The one which is labeled FM, which has essentially only phase noise, the difference is 0.3 or 0.0. And that's the measurement accuracy of the FSUP. I don't get decimals at 1 kHz, but it does give decimals at 10 kHz. The unit that stands out is the one with a lot of amplitude modulation, labeled AM. At 1 kHz they differ by 4 decibels. With the FSUP it seems to be more noisy than it really is. So the strong amplitude noise, which is only minus 133, that's about 10 decibels more noisy than the, 14 decibels more noisy than the phase noise. While at 10 kHz the FSUP gives minus 155, and the amplitude noise is very much stronger. But the phase noise is at minus 167, so the FSUP measurement is degraded by more than 10 decibels by the presence of this strong amplitude noise. And I can trust Linrad pretty well when it comes to discriminating against AM modulation, because it's a digital process which is under very strict control what I'm doing and not. And how the FSUP avoids the phase detector they have, or frequency detector, I don't know the internal architecture. Maybe there is some it's obvious there is some sensitivity for amplitude noise in that instrument.
I am now measuring this 10 MHz oscillator from Wenzel. At 1 kHz, it is here, that is minus 170 dBc per hertz, and at 10 kHz, it's 1 decibel below that, and that's the flat noise floor. So that is 171. Here is the data sheet, and it specifies 165 at 1 kHz and 166 at 10 kHz. But the unit I have is 5 decibels better than this. My setup with the two SDR-IP units plus two 10 MHz units with a phase locking between them is fairly complex and rather expensive, the SDR-IP units. So here's another alternative if one is not looking for such extreme performance. This is a Fedri SDR net and an hybrid and an attenuator. And I have connected this to the reference oscillator here. And I'm running at the same time another instance of Linrad in another screen. And here is the result when using the Netta Fedri to measure that fairly good reference oscillator. So what we see here is the performance of the Netta Fedri. The noise floor when measuring with the Fedri is minus 144 dBc per hertz at 1 kHz, and at 10 kHz
it's minus 152. So this is good enough to measure things like amateur radio equipment and more normal oscillators.
The ephedry has to be modified, and you can find a video about that at this location. It is called ephedry correlation, and it shows here how the voltage to the oscillator has to be filtered with big capacitors. The big one is 3,300 microfarads, and there is also one with 470 microfarads.
Here is an oscillator from CTI, OSC 5A2BO2, 10 megahertz. The noise level is rather high, so I get a result very fast. This is after 7 minutes. Here is a CMAC STP2187. It's a double oven unit for 10 megahertz. The phase noise is rather low. At 1 kilohertz, it's here at minus 162 dBc per hertz. But at 10 kilohertz, it looks really funny. Above 11.5, the trace is blue, means correlation is negative. And that must be because the output impedance is very far from 50 ohms. And I also see a strong imaginary part, that's the red trace, which is really a noise signal, because noise otherwise would spread like this. Since the frequency is 10 megahertz, I can use the sound card, the UADC4. And here everything looks quite normal. So I was incorrect. The problem is not the impedance of the signal source. It is something else. I have restarted the SDR-IP units, and now it looks like this. It's perfectly flat. And I was wrong, it wasn't 10 kilohertz, it ended at about 6 kilohertz. So here is the region where the problem was. And I understand it now. Something had gone wrong. I have lost a packet. So there is a time delay between the two SDR-IP units. And at some delay, the modulation envelope will be out of phase. And there the noise will come with negative sign. So this was no mystery. But what is more mysterious is why the noise I see here is at minus 162.5, while, okay, with the sound card it is also 162.5. My memory was not right. At 1 kilohertz it should be 161.5. And at 1 kilohertz I have some problems, but 161.5 is a very reasonable interpolation between here and here. And these interferences, I don't know where they originate. I have cleared the average correlation spectrum for both systems. That's the yellow curve that I've started to collect once more. It is now half an hour, and what I see at 1 kilohertz, it's here, it's about 161.8. And at 10 kilohertz, 162.5. And this is the sound card system. And here is the SDR-IP. It's a little bit more noisy because the separation from here, the green and magenta, and down to the yellow is larger, so I need more correlation gain. But at 1 kilohertz,
I cannot really read here, but it is compatible with the noise at the sides, to say 161.8 here also. And at 10 kilohertz, so the interference I saw around 900 hertz, maybe I had knocked on the table or something to cause vibrations, and since they were not visible in the sound card, I may have started the sound card afterwards. So anyway, there wasn't any problem with that. Close to the carrier, here, the amplitude noise is stronger than the phase noise. The amplitude noise is white and the phase noise here is yellow. But at about 4 kilohertz, they are the same. And then at 10 kilohertz, the amplitude noise is going down a little bit below the phase noise. So I guess this is a buffer amplifier with flicker noise giving amplitude noise modulation. But it doesn't affect the oscillations because it's not inside the loop with the crystal filter in it. When I look with the SDR IP for this same thing, and I have to click here and here, you can see I don't see much. It's very noisy here, the amplitude noise. So if I look at the amplitude noise here, this is what the amplitude noise looks like, and the imaginary part is almost as strong. Now this is 1 decibel per division, so it's not quite as bad as it looks. And of course the reason is that there is a lot of amplitude noise in the SDR IP, in the ADCs there, at close separations to the carrier. With a larger transform size, it is now 2 to the power 18, and also a wider range for the logarithmic scale. It is wider now. One can easier see the difference between the noise floor and the spurs. So I can verify that at 1 kilohertz, 161.8 is a good value for the noise floor, and at 10 kilohertz it is 162.4. The SDR IP is more noisy but has fewer spurs, and it also gives the same 161.8 and 162.4 for 1 respectively 10 kilohertz. I can see some undulations here, and you can see also up here. Because the SDR IP is not calibrated, I have changed the sampling ratio to see all the way up to about 15 kilohertz. And the same is for the sound card system. It was also not calibrated. I have added a big capacitor from the frequency control pin on the CMAC to ground. The frequency control pin has an internal voltage divider between the reference voltage at 8 volts and the ground. But I have decoupled it now, and that has some effect on the noise. There is a difference, but it's not large. I had 162.4 at 10 kilohertz. That's here. But now it is 162.6. I have 0.5 decibels per division now. And at 1 kilohertz here, the previous value was 161.8. And, well, it's not easy to judge, and I don't have the patience to wait for a better reading. This has some influence, but it's not important. The next one is a Bliley NVR 47M 1008. When I connected this now, you can see on the waterfall it is drifting in frequency, and it was quickly reaching equilibrium, so now it has locked. But it is far more noisy as compared to the CMAC. With a very strong phase noise, I don't need any correlation. I can see that there is a noise maximum at 5 kHz, and I can see it here at 5 kHz offset. This is more red, and it's stronger on the high frequency side. So that means that it is a combination of amplitude noise as well as phase noise. And something happened at this point, you can see. The problem with this oscillator is that it is very sensitive to noise on the supply voltage on the 5 volt line. So I put a big capacitor there, and noise went down significantly. And then I made an RC filter with a big capacitor and a resistor. But that is a dangerous thing to do, because when the oven draws a lot of current, one would set the voltage a bit too high, and then when the oven switches off, voltage may go too high. And this thing is now no longer working because the output buffer is destroyed. It is oscillating. I see a weak signal, but it is very weak. So I have lost this oscillator. I should have put a Zener diode also for a protection. This one, Toyicom TCO S12 X3. It doesn't have any oven inside. I can judge that from the current it uses. It takes 12 milliamps only, and it has an open collector output. And it is sensitive to filtering on the power supply. Here was directly on the power supply. This is through the RC filter, and that is an RC filter with a time constant of 10 to 20 seconds. I don't remember exactly. Very big capacitors and a fairly large resistor. But this time I was careful to not go above the 10 volts that the unit wants to have. The noise at 10 kHz is here, 155.3, and at 1 kHz 152.5. I am looking at the CMAC STP2187 again, but this time I have a well-filtered supply voltage, 10 ohms and 800,000 microfarads. That's many seconds. So now the noise floor at 10 kHz is at 162.7, and at 1 kHz it is about 162. And I don't have the patience to wait for a better accuracy. That's not important. This is an isotemp OCXO 131 100. It's fairly flat all the way. At 10 kHz it is here 153.5, and at 1 kHz 152.5. Here is an old signal generator, an HP 6080. Vacuum tubes inside. It has been running for about 15 minutes, but it's still drifting fairly rapidly.
I can see the level at 10 kilohertz minus 145 and at 1 kilohertz minus 116. And you can see here the green, that is the mirror image spur which is moving fairly rapidly because of the frequency drift. And it's more important in one of the channels, the green one, as you can see here. And if I restart, well, there is another spur moving in the same fashion. I can see better with the SDR-IP. This is the sound card. And here is the SDR-IP. You can see the same phenomenon with the moving spur because the 10 megahertz reference is leaking through. But I see again minus 116 and here minus 146. Well, I clear it again. (116). Here is the HP 8657A. And it looks like this. 1 kilohertz minus 102. 10 kilohertz minus 127 and a half. At 1 kilohertz I see minus 102. 10 kilohertz a little better than 127. This is a rubidium clock. I don't know what make it might be, but there is this label on it. I have just started it, and it begins by sweeping up and down until it finds the resonance of the rubidium atom, and then it locks to it here. It looks cleaner on the SDR-IP because there is no image mirror, or let's say the image mirror is much weaker. The phase noise is 145.7 at 1 kilohertz with the sound card, and here at 10 kilohertz minus 154. And here is the SDR-IP, and the result is exactly the same. And the amplitude noise is much lower. This is the SDR-IP, and I have set a little too low signal level so I don't get it very accurately. In the sound card I have set the level more appropriately. So, oops. This looks ugly at 161. And to see that with the SDR-IP, I have to increase the gain of the SDR-IP. The amplitude margin is 15 decibels, so I increase the signal level by 10 dB. And nothing happens. Something is wrong. I have to exit and restart. And now the amplitude margin is 5 decibels, so it's 10 decibels more signal now. Now I can see this feature clearly, and these spurs. And if I compare with the sound card, it looks like this. But what I have here, at the same level, is hard to see because the uncorrelated signal is 4 decibels stronger at this frequency. And the structure here, that will take a long time because the
amplitude noise of the SDR eyepiece are so much higher as compared to the sound card, as you can see here, from here down to here about. But it is the phase noise that is of interest. And the phase noise is the same on both systems. This is the SDR IP, and here is the sound card. There is some odd hump at maybe 12, 13 kilohertz or so, and it's of course present in both systems. Then on the sound card, the response of the audio side in my 2-channel direct conversion receiver falls off here. There is a difference, otherwise it is the same. I'm still running the rubidium oscillator, but I have reduced the baseband sampling speed from 48 kHz to 500 Hz. And here is the result at 0.1 Hz, minus 62 dBc per Hertz, 1 Hz, minus 81, 10 Hz, minus 98, and 100 Hz here, minus 134. And this is the SDR IP. Here's the sound card. I have been running it at the same time, and the result is very much the same. Except for the spur here from the mirror image, of course. I am now measuring the Wenzel oscillator at very close range. This is difficult because an oven-controlled oscillator is a negative resistance. When the voltage increases on it, the current decreases because it wants a constant power. This means that an RC filter on the input with a big enough resistor to make a long time constant would make an oscillator. So there is a need for very big capacitors and not quite as big resistors as one would want to get a time constant well above 20 seconds. And collecting spectra is very slow. This is 3 hours and 20 minutes, and I have collected 24 spectra in this time. And this is how it looks. I can get an idea about the phase noise from 10 Hz down to maybe 0.1 Hz, but this is I don't know if it's a spur of it or if it is just random. Signal to noise is very low, the imaginary part is up here. So probably the curve goes more or less straight here. But this is the sound card, and the offset from 0 is 41 Hz, so I have a strong spur here. And then I have the overtone to that here. And there is noise on the sides of these spurs, so I cannot measure well here. I would have to wait a very long time because of these noise sidebands. That's the 1/f noise at the 0 frequency. The SDR IP has failed. Something has gone wrong. And I can see here there has been 6 events. When I look at the CPU load, I see that 2 threads occasionally go up to 100%. And it happens at regular intervals. And maybe these are drifting slightly in time, so at some point they will coincide, because the frequency is not exactly the same. It is nominally 32 kHz, but there is some little offset. I think that is the explanation.
So I will simply switch off the SDR IP and concentrate on the sound card. And I want to avoid this 41 Hz spur, so I will move it to some other frequency, maybe something like 25 Hz. Now the frequency is 9999.9698 kilohertz. Means we are very close to 30 Hz below my reference oscillators. And then the spur, of course, comes at 30 Hz, 10, 20, 30, with an overtone at 60 and another one at 90. So I should be able to see 100 Hz here if the signal-to-noise ratio were good enough. But it isn't. Anyway, I have a good result for 0.1, 1 and 10 Hz offsets. And I can see the noise here is much higher than it was when I had the oscillator set to a lower frequency. So what I have here is 75 at 0.1 Hz and 115 at 1 Hz, and at 10 Hz 147. I have changed the scales, the horizontal to linear, and the vertical is still 2 decibels per division. And the reading I could get from this is about 163. But the imaginary part is at the same level as the sideband noise signal, so this isn't really something I can trust. Now the uncorrelated noise level is about 144 here, and that's pretty high. This is now the SDR-IP unit. I have increased the baseband sampling speed by decreasing the first mixer bandwidth reduction from 6 to 5. And now I will try to find optimal parameters to look at the noise at 100 Hz. And you can see at the current settings I have from 0.2 Hz up to 250 Hz or maybe 300. So to gain speed, I make the transform size smaller. I go from 17 to, let's say, 13. And then I will see from 1 Hz up to 200 Hz. So I can make it even one step smaller than that, let's say 12. Then transforms will come in rapidly. Then I don't need this very narrow filter, so I can make the size of the third FFT smaller. So it means this arrow here, it is now 16, that is 2 to power 16. And I look here while decreasing. Here, I lost a little bit on the low frequency side, but this filter has an ugly shape. I want it to look a bit wider, like that, and then I lost even more here. But that's okay, I'm interested in the situation at 100 Hz. So I click on the signal,
and get it centered in the filter. And there is a good distance to the spurs I see. So here it's now both amplitude noise and phase noise, but I want phase noise only. That's here. And now the noise floor at 100 Hz is at minus 140. That's even worse than what I had with the sound card. So this is not going to work well. And you can see at all frequency offsets, the imaginary part and the signal is at the same level. And at lower frequencies, there are many negative values. So this is actually more or less useless. Here are the same settings with the sound card. After now 4 minutes, the noise at 100 Hz is around here. That's minus 158. And I want at least 10 decibels better, means 100 times more time. That would be 300ths. Now I waited 9.5 hours, almost. That's about 560 minutes, a little more than the 300 I expected. And I get a noisy curve, but I can yet read reasonably well at 100 Hz, something like that. That is minus 163. And as it happens, that was what I saw in the previous measurement also. And the very noisy reading I had at 10 Hz is now not noisy at all. It is minus 147. Just as I found previously. I have a big problem here. When the Wenzel is set 41 Hz below my reference, the reading at 0.1 Hz was minus 90 decibels. But now, when I shifted it by 11 Hz, it is only minus 75. That is 15 decibels. At 1 Hz, the difference is much smaller, only 2 decibels, and at 10 Hz, 1 decibel. And I guess at wider separations, the results would be the same. I have to check this because I'm not quite sure. It seems unrealistic that such a large difference is really a problem with these oscillators. It means that if it is correct, then it would be much better if the crystal was manufactured for a slightly higher frequency. I have restarted Linrad in the Meteor Scatter CW mode. That's where I had the parameters that I used to measure at 0.1 Hz offset. And what I see is fully compatible with the old value, minus 75 dBc per Hertz at 0.1 Hz. And this is with an offset of 30 Hz. I have not changed anything. At the same time, I have been running the SDR-IP in normal CW mode. That's where I have the parameters to look at wide separations. And what I see here at 10 kilohertz is minus 175.5. And that's quite odd, because I had minus 171 before, when the offset was 41 Hz. It's maybe easier to see when I change to linear scale, minus 175.5. I have repeated the close range measurement
when the frequency is 30 Hz below my reference. And it's still pretty close to 75. It's more like 76 now. But the statistics is not so good, so it's the same result. And it looks perfectly as before. I realize I have forgotten to put the screw back on the Wenzel oscillator, so the box is open and maybe it is sensitive to infrasound. The screw is in place now with its rubber washer. With only 7 averages, the signal is noisy, but it looks like 75 if I look at this straight line. So the problem was not infrasound. In the meantime, I have collected the wide range spectrum with the SDR-IP, and at 10 kHz it is minus 171 and 170 at 1 kHz. I have turned the frequency control screw counterclockwise to the end, and then the spur is again at 41 Hz. This didn't help. Noise was still at minus 75, and I have erased that, so I cannot show it, but that was the case. Then I have removed this fuse and measured it and put it back again. And that made a difference. It is now much better. Not quite 90, but clearly below 75. I have eliminated the fuse. And now, at 0.1 Hz, I see minus 86 dBc per Hertz. But the imaginary part is not well below the curve. It's here and here. And yes, they are not so close spaced. This one is well below, but not here and here and here. So it is not any accuracy of this curve, although I have been waiting for 6 hours now. I'm tuning the Wenzel oscillator to give the same frequency as the one I have from the rubidium source. So then I know I will be more or less exactly on 10 megahertz. Something like this. It is drifting slowly. This is the frequency, 9999.970729 kilohertz. That's an offset of 29.71 hertz from my reference oscillator. And this is close to the 30 Hz I had before, so I will check that I have still the performance that I am thinking now that is independent on the frequency offset. The problem I had with the fuse is probably a problem I have had for a long time without knowing. So for the future, I will do like this. I have soldered the fuse, and I will have to resolder next time I break it, because when measuring on experimental oscillators, I now and then happen to touch something, and without the fuse there is a big boom, and I have to replace all the small inductors and other things that evaporate. Now the noise level is even higher at 0.1 Hz, minus 72 dBc per Hertz only, and there is no correlation advantage anymore. The red dot was high above the blue when the measurement was down here somewhere. I have turned the frequency adjustment screw to the anti-clockwise end position, and again noise is low. It's minus 88, just as before, and I can see the red dot far above the blue dot, representing my oscillators in channel 2 and in channel 1. And of course the spur has moved back to 40 Hz, or 41 probably. I have connected the STP2187 from CMAC. It has been running for 4 hours now, and it's still drifting upwards in frequency, gradually slower, but still not very slow. It's 0.1 Hz from here to here, and you can see 0.1 Hz is about 10 minutes now, and it was a bit faster several hours ago. So I will leave it and see whether it will stay on frequency so I can do the close range noise measurement. I can see from the spectrum that the close range noise is good. From here to here is 100 decibels almost, and that indicates that the noise at 0.2 Hz is significantly better than what I have seen from the Wenzel just recently. But of course not when the Wenzel was in the lowest possible frequency, but when it was at 10.0 MHz. The CMAC has been running for 8 hours now. It is still drifting upwards in frequency, but it's not drifting so much that it gets too far outside of the filter. It will come to something like here, maybe 6 decibels below the peak amplitude. So I start a measurement here, and I have collected just one single correlation spectrum, and it starts at minus 70 at 0.1 Hz. Tomorrow maybe it has a fixed frequency, and I will have a reading on the graph, and I will reset and see if it changes, because now it's 2 o'clock in the morning and I'm finishing for this day. The CMAC has been running for 16 hours now. It is still drifting upwards in frequency, but it isn't drifting more than that it is keeping within the filter. So now it is close to the point where the Linrad AFC will move the frequency and bring it back to the center. And during that time it will switch off the averaging, so it will collect the proper phase noise. But the curve I have here is collected when it was still drifting much faster. So I will clear it. I have taken down the numbers, 72 at 0.1 Hz and 104 at 1 Hz and 136 at 10 Hz. So I clear this. Well, now it has switched to the center frequency again, and it will take some time before it has collected the first average spectrum. The frequency drift I see cannot be a thermal problem. It must be aging of the crystal, or maybe aging of something else. I don't know. And I don't know whether this is normal, but it's something that I observe anyway. In parallel, I have had the SDR-IP running and collecting spectra at a slightly wider bandwidth. And here I can read for 100 Hertz, 158 or 158.5 maybe. And here comes the first average spectrum, and we will see when there are several of them collected. It comes when the frequency is here, so it is properly centered in the filter from which the carrier is extracted. 2.5 hours gives good statistics. I still see 72 dB here at 1 Hertz, 105. I said 104 previously. Well, and here 137. That's 1 decibel better. And at 100 Hertz, 158. So the previous result was not bad, although the frequency was drifting very much at the start of that measurement. I have remeasured the CTI OSC5A 2802. This time I find better results than before, a significant difference, 5 decibels, as compared to what I found here. What I have done is that I am feeding it with 7.5 volts from a well-filtered supply. There is an RC filter with an attenuation at 0.1 Hertz of more than 10 decibels. I can have a bigger resistor than I could have with the CMAC, because this is less prone to oscillations due to the negative resistance of the oven circuitry. And I did some more experiments, just with the supply RC filter. I have these numbers. Then I have added a 0.1 farad capacitor on the 5 volt regulator. That improves at 0.1 Hertz, but it doesn't affect higher frequencies. Then I added 4,700 microfarads on the pin of the oscillator that controls the frequency. And very small, maybe insignificant differences, 1 dB and half a dB. So I'm uncertain whether this had any effect. The impedance at the control pin is very high, so this capacitor has a dramatic consequence, which I will just show. After I added that capacitor, the frequency was drifting, and it took maybe 20 minutes until it became stable. And that is probably a very much too large capacitor, 4,700 microfarads. But to evaluate what would be the optimum, I would need to look at Allan variation. This spectral analysis is not good to look below 0.1 Hertz. And here is the spectrum I see with the CTI oscillator. It is nearly 3 hours, and 74, 110, 135, and finally 146 at 100 Hertz. And the wider offsets from the SDR-IP at 1 kHz, 151.4
and 10 kilohertz 153. I can look at the amplitude noise, and it increases at wide separations, as you can see. This is unusual. I don't know what this really means, but when I look here, I see that amplitude noise and phase noise are strongly correlated at 2 or 3 or 4 up to 10 kilohertz. And the phase angle between the modulations is 90 degrees here, and at some point it starts to, probably at 50 kilohertz, it will be 45 degrees. 0.1 farad directly on the 5 volt regulator seems to be a good thing for very close range. That means stability in 10-second and maybe longer time scales. This capacitor, on the other hand, is questionable. 4700 microfarad may be far too much, and whether it makes an improvement at all is a little bit uncertain. Now I look at the close range noise of this oscillator. Frequency stability is not particularly good. You can see the white horizontal lines. That's when Linrad makes a frequency adjustment to keep the carrier at the middle of the filter. Such a thing happens right now. But I have collected the phase noise from 1 Hz and upwards up to 1 kilohertz. And at 1 Hz I see minus 80 decibels. And 10 Hz it's 117.5. 100 Hz minus 149, I think.
This is an experimental oscillator. These structures look like cooling flanges, but they are not. They are to make the box stiff to keep infrasound out. This doesn't work properly at the moment. There is a bad connection somewhere. I think it must be one of the trimmer capacitors. But that's not the point at this moment, because the effect of that poor connection comes only very close to the carrier. This and also these other structures. I don't think these are the frequency changes, maybe, but this is definitely an interference burst. It should be around 90 or maybe 86, but it is at 72 at this time. And this is the close range, which is not nice. But at the same time, I'm looking at wide separations from 1 kilohertz up to 10 kilohertz. And here I don't see the noise floor yet, although I am down at minus 186. I can see better if I go to a compressed linear scale, so I click up here, linear, and then I see that I don't see the noise floor yet. Here at 10 kilohertz, I see the imaginary part is fairly high, and there are many red points down here. I have to change this vertical scale like this, and now I can see that the imaginary part goes from here to about here. So signal-to-noise ratio is still not at all good enough, which means that I would say that probably the noise floor is at the least below minus 189, maybe even a little bit lower. So this has to be measured by other methods, because very high correlation gain like this could be inaccurate. This oscillator uses at this moment one 10 MHz third overtone crystal. It can use 2 crystals, and that improves by 3 decibels, maybe more, I'm not certain. But there are problems with it. So if you are interested, this is in my series of videos for nerds only. Those videos for nerds only show various experiments I'm doing to try to optimize various things. For example, this oscillator. In a compressed linear scale, it looks like at 100 Hz, below minus 164, unknown how much below. Here is a summary. These first measurements confirm that the scale I have and the programming of Linrad is correct, because they agree very well with the old measurements with the FSUP back in 2009, except for this oscillator with a deliberate design error, one that is common in amateur radio, and it has high amplitude noise, and the FSUP showed then too bad phase noise. So it probably mixes a little bit of the AM noise into the phase detector somehow. Then an interesting thing is that the Wenzel oscillator is much better if I place the tuning screw at the end position. When it's tuned away with 11 Hz, it is at minus 88 dBc per Hertz at 0.1 Hz. And that is very good. But when I tune it to 10 MHz, it is degraded down to minus 75. And then the best here and here, that's the Wenzel. And the Wenzel is the same when it is tuned to the proper frequency. Well, nearly the same, 118, 116. But the stability over 10 seconds and probably over longer times suffers if I tune it to the right frequency. I guess there is something with the noise on the capacitance diode. Maybe the trimmer has a too high resistance, so there is noise from the resistors. And then this experimental oscillator, which is far better than anything else at wide separations, but which has a problem at close range. And at 1 Hz, it's about the same as the Wenzel, and going above at 10 Hz, it is significantly better.